So we're going to start section 13.6, which is about directional derivatives and gradients. So we're going to start with directional derivatives. So we're going to assume that we have a surface that's given by an equation. So consider the surface given by z equals f of xy. And I want us to start by recalling some facts that we've previously discussed. So we previously said that the slope in the x direction is given by the partial derivative of f with respect to x, and also the slope in the y direction is given by the partial derivative with respect to y of my function f. So those were two things we discussed back when we were doing partial derivatives. But what I want to say is now what we want to do is we're going to find the slope in any direction, not just the x and y direction. So in order for us to talk about a direction, we're going to need a unit vector for our direction. So I'll say the direction of the directional derivative is given by a unit vector u. So this is going to be a vector in the xy plane. So if my vector u comes out on my xy plane, I know the length of this vector is 1 because it's a unit vector, and so I can describe this vector using this angle theta. It's going to be cosine theta I plus sine theta j. So now that I have a direction, this vector u, we can define the directional derivative now. The directional derivative of f in the direction of u is, I denote it by d and then a subscript uf, is given by the following: du f, it's the limit as t goes to 0 of f of x plus t cosine theta y plus t sine theta minus f of xy over t. So this is a derivative, so the way it's defined is in terms of a limit, but we don't have to compute the directional derivative using that limit. So I will say if you know that your function f is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector u, which is going to be cosine theta I plus sine theta j, is given by it's the partial derivative of f with respect to x times cosine theta plus the partial derivative of y times sine theta. So this is the formula we're going to use most often because in most of our examples, f is going to be a differentiable function. And I do want to mention that this directional derivative here, this is a scalar. It's not a vector because we're taking the derivative in a particular direction, we get a scalar and not a vector.